Welcome everybody. Today we will have the last lecture of the 4 lectures. The 4 Physis lectures in analytic metaphysics. Within the context of the Physis summer school, Peter has been talking about combinatorial possibilities, some issues, some options. Yesterday he provided some keys to understand modality in terms of combinatorialism, improving the theory of his former teacher, David Armstrong. And today he's going to talk about the relationship between modal combinatorialism and, as the title of his last lecture says, determinables and the philosophy of mathematics.
My version of structuralism concerns conceivabilities. This is not a radical position, that mathematics is about what is conceivable, but that includes a part of mathematics that concerns possibility, and in turn some parts of mathematics that concern possibility concern what is actual. Other parts are merely possible fictions, and yet other parts merely conceivable impossibles. So I'm going to provide a comparison between structuralism in mathematics and fictionalism, and a defense of structuralism. I then amend structuralism to obtain what I'm going to refer to as objective conceptualism about mathematics. Mathematics concerns concepts, but the concepts are objective and mind-independent. So, one important idea is this Frege abstraction. Let's look at an example. Frege uses parallel lines, but I think a better example is the idea of shape. And let's assume we have Euclidean space. There are ways of transforming space to itself. You can translate, you can rotate, you can reflect, or you can dilate. And there's therefore an associated relation between regions, namely being similar or the same shape, because that is what is preserved by translation, rotation, reflection, and dilation. So we have this relation being similar to, and because this is a symmetric transitive relation, by Fregean abstraction, there are, for every equivalence class, there are shape properties, where the members of each equivalence class share the same shape property. A complication is that some of shapes are fictions. The easiest, though most controversial examples, I suppose, are obtained by starting with nice, easy shapes, circles, squares, etc., and consider the join of infinitely many of them chosen at random. You know, a circle here, a square there, choose them at random, infinitely many, you get a shape that is a fiction. Or as those who prefer to do their philosophy in the paradoxical, poetical style would say, a shape that is no shape. More striking examples use the axiom of choice are provided by the Banach-Tarski theorem, whereby a sphere over here has 5 parts. Each of these parts are of the same shape and size as 5 parts over here, but these 5 parts over here are arranged into 2 spheres, 2 in this sphere and 3 in that one. And the result is that we have 1 sphere here, rearrange the parts, we have 2 spheres of the same size. It's magic. That's the Banach-Tarski theorem. I think you can see that the shapes you have to divide the sphere into to get such magic must be ones that are mere fictions. They're just too messy. Okay. Similarity is, in this geometric sense, is a genuine relation, but the property being similar to something isn't always a genuine property. I called it a relative concept. So the property of being similar to one of these two complicated shapes would be a relative concept but not a genuine property. But in many cases, such as being similar to that shape, that object, you get a genuine property. I now generalize. By a pre-equivalence, I mean a transitive symmetric relation. So I don't suppose reflexivity. Recall that the definition of equivalence relation is it's transitive, symmetric, and reflexive. Reflexivity fails for similarity because although every region is similar to itself, there are plenty of things that are the wrong kind to be similar to anything. Numbers, for instance. That's why a number is not geometrically similar to itself. That's why similarity is what I call a pre-equivalence. Here's my statement of Frege abstraction. If we have a pre-equivalence relation, Rxy, then there is a determinal property which could be characterized either as X stands in R to itself or as there is some Y such as Rxy. The two are equivalent for a pre-equivalence. That's the determinal property. In the case of similarity, the property of being shape is then the property of being similar to itself or equivalently being similar to something. The determinants are the real or fictional properties such that necessarily X and Y have the same determinant if they're related by the pre-equivalence. So you have the same shape if and only if they're similar. Determinants of a determinable are sometimes themselves determinables. That's part of the puzzle, if you like, of determinants of determinables. We can consider this by considering not by considering just translations, rotations, and reflections, that is, ignoring dilations. So then we get a different pre-equivalence, congruence, and for a given shape, regions with that shape differ as regards size, with X and Y being the same size if a congruence maps one to the other. In that way, we get size determinants, and we get this nesting of, we have size determinants, we have shape determinants, and then we have the size and shape together. That's how you get the structure of determinants within determinants. The details are straightforward. And students are introduced to the idea of determinants and determinables. Usually they're given the example of colours. Now colours are maybe not genuine properties because they might be too anthropocentric. Nonetheless, we'll use that as an example. So consider uniform, if you like, down to sizes of order wavelength or something, optical properties of opaque matte surfaces, and simplifying somewhat, call these optical properties reflectances. Then there's a relation between reflectances which holds if a surface uniformly instantiating one cannot be distinguished against a background uniformly instantiating another. In terms of that relation, we can define a pre-equivalence of being indistinguishable from the same reflectances. You see how we're building this up in a somewhat anthropocentric way based upon indistinguishability, but that is how it should be for colours. Okay, this is a general way of constructing a pre-equivalence, and anyway, in this case, the pre-equivalence is an equivalence on the reflectances, and the corresponding determinable is being uniformly coloured. Its determinants are shades of colour. Okay, so much for determinants and determinables. A comprehensive discussion will look at all the other accounts that have been given of determinables and determinants. I just invite you to look at them and see that the problems that are posed are handled with this account. But let's get to numbers. In his famous paper, What Numbers Could Not Be, Paul Benacharev points out the arbitrariness of set theoretic constructions. Well, that's sometimes a valid criticism. So von Neumann constructed the ordinal numbers as empty, the set of empty, the set of empty, empty, etc. This corresponds to a set of lectures on the ordinal numbers in which they are shown rather than said, in which in the first lecture the professor says nothing, and in each lecture the professor recapitulates everything said in the previous lectures. This gives you the ordinal numbers. Well, it doesn't, of course. What it gives you is one instance of a certain order type. When we think of ordinal numbers, the thing that von Neumann constructed is clearly an instance of something. It's an instance of a certain order type. And we can have other instances of that order type, especially easy to think of when we're considering finite ordinals, because the cardinal numbers, cardinal number, 0 is a cardinal number, isn't it? 0, 1, 2, 3, etc., also exhibit the same order type as the finite cardinals exhibit that same finite ordinal type. Things are much more complicated when we get to the infinite case, but that doesn't affect the general issue. In the same way, I would criticize as arbitrary Kuratowski's set theoretic construction of the pair. I wrote that down the other day. Now, the structuralist responds to the problem of characterizing ordinals, and the more general problem pointed out by Bonaccia, one of his problems, is to replace ordinals by the order type. Thus, in place of the finite ordinals, we consider the structure shared by any system of countably many items ordered in the same way. It's easy enough to describe the order for the finite ones, and fairly easy even in the infinite ones. You know, it's familiar. Generally, given any category in the mathematician sense of category, it doesn't matter exactly what that means, it just means a mathematical kind, so it's not as all-inclusive as a philosopher's sense of category, but it just means a kind of mathematical object in mathematics terminology. There is a pre-equivalence defined by isomorphism in that category. So, pure mathematics, well, take algebra if you know any algebra, not that you have to know algebra. Algebraists have all these sort of wonderful abstract things. They talk about groups and so on. Rings are an especial favorite. There's a lot of theory of rings. These are abstract structures, whatever that means, we'll come to that, of a certain kind. And the isomorphism is a one-to-one onto mapping that preserves that kind. And the definition given in category theory is slightly different, but that doesn't matter. That's the sort of paradigm of an isomorphism. There are other isomorphisms, but the paradigm is of a one-to-one mapping between one mathematical structure and another that preserves the structure, so that there is an isomorphism. It's pretty trivial, but there's an isomorphism between the cardinal numbers 0, 1, 2, 3, etc., and von Neumann's constructed ordinals, his example of the ordinals, and it's, in the finite case, it's a one-to-one mapping that preserves the structure, but in that case the structure is just the ordering relation, one coming before the other. So that's an isomorphism. An isomorphism is always a pre-equivalence. And, well, no, it's, yes, it is always a pre-equivalence, but that's, the symmetry might not be obvious, but it's part of the stipulation of the definition of an isomorphism in category theory, that it's symmetric, it's got an inverse. So, by forgetting abstraction, we get the mathematical concept. So for every category in the mathematician's sense, any kind of mathematical structure, there's isomorphisms, and so there's a corresponding property of being of that structure. as the structuralist response to Bonatereff's problem. The alternative to structuralism, or at least the feasible alternative to structuralism, might be to treat the ordinals as fictions without attempting a construction. So you say, instead of saying there are many examples of this order type, you say, no, there is such a thing as the ordinals, but it's a fiction. Fictionalism in mathematics has common, and that's why we can't say it's this set theoretic construction, because that would be a different fiction. This is just a sort of fiction. We just suppose we've got these things ordered in this way. Now, fictionalism in mathematics has common sense appeal. The folk are reluctant to believe in pi. They're reluctant to believe in negative numbers. When I say that around about 800, Brahmagupta discovered negative numbers, the folk tend to respond, no, he invented them. But no, I say he discovered them, so I'm a realist. But what about complex numbers? Now, as you may know, if you have studied some mathematics, and why should you have, but if you have, when you look at complex numbers, the number I, the square root of -1, or one of the square roots of -1, that itself is a structuralist issue because they're two and you don't know which is which. The square root of -1 is called I. And it's called I because it's sort of, it was just called imaginary. So when complex numbers were first discussed by mathematicians, they thought they were inventing them. They thought they were fictions. They were used to help solve equations in the, I think, 16th century, something like that. People like Tartaglia in Italy. They were thought of as fictions, but I know better, they really are complex numbers, or so I say. Now, fictionalism and structuralism are in fact compatible. The actual practice of mathematicians is to talk in a strangely Platonic way, Platonist way I mean, of the ordinals, the real numbers. It's a bit like the good. And if you talk about the ordinals, you seem to be referring to fictional paradigms or exemplars of universals, that is types, that may well have non-fictional instances, and in applied mathematics clearly will. You might think that the practice of mathematicians is sort of to combine the two, because they keep on talking about the real numbers rather than a real numbers, etc. In spite of its common sense appeal, I reject fictionalism in many cases. For example, the system of all finite ordinals, and also for that reason for the first infinite ordinal, omega. The argument is much like the argument for realism about other universals. A classification based on ordinals would be judged natural. For larger ordinals, the case is far from clear. There is a branch of mathematics to do with the transfinite, and there's, it's rather fascinating. There's actually quite a good book on it called The Joy of Sets. Maybe all uncountable ordinals are fictions. Once when David Lewis was asked what's the maximum size of a possible world, he said there shouldn't be more than Beth omega entities. And if you look up this theory, you'll see that Beth omega is an extraordinarily large number. Okay, but maybe after that they're all fictions, because they're even larger ones. There's a whole theory of these things. There's a theory of inaccessible cardinals, which doesn't mean someone that only Opus Dei can talk to. Anyway, if so, we can only make an educated guess at which countable ordinals are real. It's an educated guess. I would say the recursive ones, if you know that stuff. But my point is not that. My point is we neither know, should expect to know, precisely which mathematical structures are real. The case against fictionalism generalizes to something like the familiar indispensability argument of Quine. Quine argues in favor of of some mathematical existence of some mathematical entities because they're required for physics. Now, I don't say that mathematical universals are indispensable. Part of my reason for that is what I've elsewhere called fundamental nominalism. But part of the reason is you can see, for example, the way Hartree Field looked at Newtonian mechanics. Perhaps with a bit of ingenuity, you can dispense with them. My argument's slightly different. My argument is from the way theory choice in physics is based either on simplicity or aesthetics. An elegant theory has an elegant mathematical description. So theory choice would be descriptive relative and subjective unless the mathematics used in physics is in some sense more objective, some objective sense, more natural than messy alternatives. Kepler was right, for instance, to prefer ellipses to epicycles. Okay, now I want to, so that's some sort of case for structuralism and why structuralism is preferable to fictionalism as a response to Banachev's rejection of specific set theory constructions in mathematics. There's nothing wrong with set theoretic constructions, but they just give us one instance. They don't give us the instance of a mathematical structure. Stuart Shapiro distinguishes three kinds of structuralism. I'm going to argue for a fourth. Maybe it's just a modification of one of these kinds. It doesn't matter. So we have the same sort of reasons for believing in mathematical structures or some mathematical structures. I already suggested some of the more rarefied ones, such as large infinite numbers, may just be fictions, but with the same sort of reason for believing there exist mathematical structures as for other universals. Now, Shapiro considers Banachev to be a nominalist. He identifies an Aristotelian position, that of Hellman, which takes mathematical truths to be about possibilities, and Hilary Putnam said something similar. Granted the combinatorial theory are possible, Hellman's position collapses into structuralism in the narrow sense, that of Shapiro himself and of Michael Resnick. As the examples of the ordinals suggest, some of these structures should be considered real, others merely fictional. So the idea of structuralism is that mathematics is about the universal types that the so-called mathematical categories, what we would just think of as mathematical natural kinds rather than categories, namely natural kinds, exemplify the structure. And two members of a kind exemplify the same structure if they're isomorphic. So, for example, the, let me get this right, fairly obvious is trivial, but it generalizes to something non-trivial. The ways of rotating a tetrahedron into itself and one-to-one correspondence with half of the possible permutations of 4 items. Because if you list the permutations of 4 items, you get 24 of them. 12 of them preserve parity, and those correspond to the group of rotations of the tetrahedron into itself. The other 12 are obtained by reflecting the tetrahedron, as well as rotating. So that's an isomorphism. It's the same structure. So the idea is that mathematics, according to Shapiro, the structuralism in the narrow sense, mathematics is about those universals which are structures in that sense. Now, as a variant on that, or fourth position, is what James Franklin, developing David Armstrong's idea, calls Aristotelian. But because Shapiro, who's something of an authority on the subject, calls Hellman's position Aristotelian, and because in any case some so-called Aristotelians like me believe in uninstantiated universals, I'm going to call it Newtonian structuralism. Because Newton uses these ideas. Now, I recently read something that suggested Euclid does as well. So if we're going to be really pompous, we might call it the Newton-Euclid theory or something. Anyway, it goes beyond structuralism in the narrow sense by claiming that mathematical structures sometimes have non-fictional, that is, real instances, which are still mathematical things. That's the difference. If you're Shapiro, you think of mathematics as about universals, and you think of the instances as applied mathematics, the structures as applications in physics. The only difference, and perhaps it isn't that important, I don't know, with this position I call Newtonian, is that in fact some of the instances of mathematical structures corresponding to these mathematical kinds, which mathematicians call categories, are recognized to be mathematical things. The clearest example of these are the natural numbers themselves, the positive integers, and the real numbers, which I discuss in the next section. These are not properties of characterized by isomorphism classes. We know the isomorphism classes. I remember being taught this. We know the isomorphism classes. We can show that any algebraic system that has the following properties, they're about 5, I think, is going to be isomorphic to the real numbers. That's the rational and irrational numbers put together, the real numbers. But the point is this, if you're Shapiro, you would say that's all there is to the real numbers. The real numbers just is that structure of obeying these axioms. And you can show that anything that obeys these axioms are isomorphic to each other. But I would say no, actually there is a particular case of what the real numbers are, but in itself is something recognized to be mathematical, but it's a particular, it is an instance of that structure. So in that case, the real numbers turn out to be universals. In fact, they're second-order universals. But the structure that Shapiro thinks of as being the real numbers, which I think of as just being isomorphic to the real numbers, is then a third-order universal. Okay, once we grant these cases, we can then make an educated guess as to where reality ends and fiction begins. But it's only an educated guess. I suggest complex numbers are genuine reals, quaternions are fictions. Finite dimensional real vector spaces are non-fictional, but infinite dimensional ones fictional. Now let's now expound Newtonian structuralism, as I called it. Newton considers the real numbers to be ratios of quantities. So I consider them relations between the determinants of a suitable determinable. These ratios are themselves determinants of a determinable ratio, being a real ratio, which I identify with the real numbers being a real number. Being a real ratio is just to be a real number. The real numbers are an instance of a mathematical structure, complete ordered field. That's what I was talking about, those axioms. Anything isomorphic that is not a ratio of quantities is a further instance of that mathematical structure. The set theoretic construction, the benoited set theoretic construction of reals, the sets of rational numbers, is another instance of the mathematical structure of which the real numbers is an instance. So it's isomorphic to the real numbers, but it's not the real numbers, because rational numbers are real numbers, so sets of rational numbers are sets of real numbers, and we can't construct the real numbers as sets of real numbers. What we construct in that way is something isomorphic. Generally, set theoretic constructions provide instances of any real mathematical structure without being the structure. Now I ask, would the real numbers please stand up? Which are the real numbers? Well, let's work it out. Let's consider volume and diameter. These are determinables, and unlike many of the things discussed in physics, they're part of the common sense and manifest view of the world you have prior to doing physics. the ratios holding between many of the determinants of volume. I say many, not all, because you have awkward ratios like 0 to 0 and infinity to infinity. Likewise, there are ratios between many of the determinants of diameter. The basic idea of Newtonian structure is that a given ratio of volumes is the very same relation, not isomorphic, but the very same relation as some ratio of diameters. So if one thing is twice the volume of another, then the relation between those volumes is the very same thing as one thing being twice the diameter of another. The basic idea of Newtonian structuralism is that a given ratio of, I said it, sorry, I've already said that. Products of ratios can be defined. The addition and ordering of non-negative ratios is easily defined using volumes. The thing about this is quite interesting in a way. Products of ratios are defined easily for any kind of ratios. Addition and ordering are actually defined using the paradigm case of volumes. It's in terms of volumes that you can define. You could use mass or weight, but volume seems more fundamental. And you get the so that provides an ordering. It's just that relation that holds in general the addition and the order. You've got three things on. You've got multiplication, addition, and you've got the ordering, one being greater than another. So you have these relations of addition, multiplication, and ordering between the ratios, which are themselves, of course, higher order universals, being relations between determinables, determinants, I mean. They're characterized by reference to just one of the determinables, volume. I said you could use, you notice you get the same thing if you characterize them, say, in terms of weight or mass or something, but they're characterized that way. Now, how do we get negative numbers? As I say over and over again, because I think his name should be lauded as a very great discoverer, Brahmagupta actually used the idea of debt as negative asset, which is really rather prosaic. I prefer to consider vectors to get negative numbers. Okay, what's a vector? It's a translation of a flat space or space-time. That's a paradigm vector, the translation vector. So we have a pre-equivalence of being a translation in the same direction, right? That is a translation, but so is that. One's bigger than the other, but in the same direction. Now we can consider ratios of translations in the same direction. That is twice that. And those ratios are the very same relations as the ratios between volumes. And in this case, the addition of quantities, which we characterized in terms of volumes, coincides with the composition of translations. The summing two quantities, which we characterized in terms of volume, coincides with the summing of two quantities characterized in terms of translation. That's a feature of the world. It's not a probably not a necessary truth, but it's, if it is, it's not really to do with mathematics. Now, translations, though, unlike volumes, have inverses. The operation of moving from here to there has the inverse, the operation of moving from there to there. And so, if you are considering translations in a certain direction, the inverses are translations in the opposite direction. And now, if you consider directions and their opposites, you get the negative quantities. Because the ratio between a translation in that direction of a certain quantity and a translation in the opposite direction, namely its inverse of the same quantity, the two cancel each other out. The ratio between two translations that cancel each other out and get you back where you started is -1. So that's how, this is how on this Newtonian scheme of things we get the negative numbers as genuine, real relations between determinates of various different determinables. So you have lots of systems of determinables, but some of the relations between them, the ratio relations, are the same universal in the different cases. Okay, well, perhaps I should say something about cardinal numbers. The positive integers are an instance of a certain structure specified by the Peano axioms. They have several instances that are real examples of this. The finite ordinals, the finite ratios that are instantiated by volumes of disjoint sums of regions of equal volume. And there may be some other instances. So there's also the cardinal numbers. It understood either pre-theoretically, when you count members of a kind, or as properties of sets. Well, not actually, you shouldn't really say count members of a kind. You see the number of members of a kind because it's a bit of a mistake to introduce counting when you're talking about cardinal numbers, because counting is a ordinal thing. But when linguists and philosophers of language talk about count nouns, they're really talking about types for which you can assign a cardinal number. And as we know, for small numbers, we humans up to about 7 or something can just see the number. Rats can do that as well, and bees, and I think, and so on, without having to count. But anyway, okay. So what we mean by the cardinal numbers is just one instance, one mathematical instance of a type, a structure specified by the Peano axioms, of which some of the real numbers, which are defined in terms of quantities, form another instance, the real numbers 1, 2, 3, etc. It's sometimes important to distinguish the real numbers 1, 2, 3, etc., defined in terms of ratios of quantities, from the ordinal numbers 1st, 2nd, 3rd, defined in terms of an order type, and from the cardinal numbers. Pre-theoretically, we do not ask how many things there are, but how many f's, where f is a sortal, and the answer, or count noun. The answer is a cardinal number. Now, mathematicians have characterized cardinal numbers as properties of sets, or but the two are related. Given a property, we may consider those x that are sums, property f, sums of f's, something Armstrong does, for instance. We can now consider a relation between two particulars if they are the same f. Now, we've got to be careful here. The same f doesn't mean the same thing which is an f. Now, that relation, so we have distinct things which are the same, which are, as we say, the same f, okay? How we analyze that, we're not saying they're the same thing, but there we say they're the same f. I'll come to an example in a second. Now, if this is a preequivalence, and then we consider the abstraction, and the property is x being an f, which we call a sortal or a count noun. Now, I don't distinguish the two, but maybe we should. For example, consider the property of being the sum of particles arranged catwise, if you like, molecules arranged catwise. Peter Geach's problem of 1001 cats is based on the way that Tibble, I'm renaming the cat Tibble. In Geach's example, the cat's name is Tibbles, but my cat's called Tibble here. Supposedly a single cat is in the room. We can understand that. Tibble's in the room. Then there are thousands of overlapping sums of molecules arranged catwise, each of which has as good a claim to be Tibble as every other one. Does a partially absorbed protein in the stomach count as part of Tibble or not? Does a hair that is in the process of becoming detached count as part of Tibble or not? So instead of one Tibble with an uppercase T, it would seem there are many Tibbles with a lowercase t. This problem is resolved by taking a given cat Tibble to be a property. This bears, by the way, on the topic of how do I know I'm not a universal? The answer is, on this view, you are a universal. Or at least your property may be a fictitious one, but your property, all right. There's a given cat, Tibble with an uppercase T, is a property shared by all the Tibbles. Ignoring for exposition the complication due to the persistence of cats over time, I mean, I've dealt with that elsewhere, we can consider the relation between objects that holds if they are both Fs, or both cats, and their intersection is also a cat. So, no, F is not, okay, if F isn't being a cat, I'm getting a bit confused, F is being the sum of molecules arranged catwise. So we can consider the relation that holds between two objects if they're both molecules, sums of molecules arranged catwise, and their intersection is also a sum of molecules arranged catwise. In that case, the sums of molecules arranged, now, if it works, I mean, it's contingent that that isn't a preequivalence. But in the case of sums of particles arranged catwise, it is a preequivalence. You can't always guarantee it will be a preequivalence. Think of a banyan tree or something. And the corresponding determinable property is being a cat. So in that view, Tibble, an instance of a cat, is a determinant of the determinable being a cat. This is a bit like porphyry, actually, the tree of porphyry. It's a property of sums of molecules arranged catwise. Now, we count cats by counting determinants. Being Tibble counts once, being Bruce, that's David Lewis's cat, once. We don't count the very large number of instances of Tibble. We don't count the very large number of instances of Bruce. We count the determinants. There's a further relation that holds between sortals, or count nouns, I don't know which I'm talking about. If any intersection of an F and a G is itself both an F and a G, if that's an equivalence relation, then we can say that F and G sort the same way. For example, if F is being a sum of molecules arranged catwise, and G is a sum of molecules arranged animal-wise, F and G sort the same way, because any intersection of them is itself both an F and a G. Any intersection, this is trivial in this case, but any intersection of a cat and an animal is itself both an F and a G. It's interesting to consider, harking back to Locke, what you say about the sortals being human and being a person. If, like Locke, you distinguish the two. Any intersection of a human and a person is itself both a human and a person. So if we're ignoring time, as we are in this discussion, that's an equivalence relation, namely the relation between, there is an equivalence relation between sortals of this kind. So we can say that being human and being a person, if we ignore time, sort the same way. And sorting that way, there's a corresponding property, maybe a fictional one, obtained by abstraction. The property that things have if they sort the same way as F and G, etc., or to take a slightly more concrete example, if they sort the same way as being human and being a person. That's an abstract sortal, namely a sortal abstracted from the details of how the sorting is carried out. The point of an abstract sortal, which is obtained by Phrygian equivalence, is that we don't consider how the sorting is done, it's just we sort the same way in all the cases, so we have a preequivalence. I now submit that a set is the sum of things abstractly sorted, and the cardinality is the number of parts of that sum thus sorted. Gets a bit complicated. Let's consider the sum of some human beings. Then we can sort them as animals. We can also sort them as conscious systems. As the same as the Lockean example, we can sort them, roughly. Supposing the two coincide, then we can sort the sum of humans abstractly. In fact, we can sort them abstractly even if nothing coincides with it, but that's a degenerate sort of case and is confusing. Suppose the two coincide. We can sort the sum of humans abstractly. We're not sorting them as humans or sorting them as conscious systems. We're just sorting them in an abstract way where the abstract sortal is obtained by Phrygian equivalence from the preequivalence relation, sorting the same way. Okay. Now, as a further preequivalence of being in one-to-one correspondence, where the sum of some f's corresponding in this way to the sum of some g's, if there's a relation R and x is a part of u that's of f, etc., just read it. It's the, I'm not going to read out all that mumbo jumbo in terms of symbols. It's all based on Hume's principle, the principle that you go to a restaurant and you say, I see the number of forks is the same as the number of knives, and someone says, how did you count them so quickly? And you say, I don't have to count them, I can just see that for every knife there's a fork. That's Hume's principle, that's what I'm relying on here. So the sets have one-to-one correspondence. One-to-one correspondence is another preequivalence, and the property obtained by Phrygian abstraction from one-to-one correspondence is the cardinal number. A special case is that in which I built into this, I built into this the fact that we're not talking about all the human beings, but just all the human beings that are part of a certain mereological sum. Because obviously when we assign cardinal numbers, we assign cardinal numbers we don't just need a sortal, the things we're counting, we also need a region. We don't just count human beings. If I ask how many human beings I'm not just interested in the answer a bit under 10 billion. I'm interested in the answer, I might be interested in how many human beings are there in this room, in which I expect to get the answer 8. So when you assign cardinal numbers, you have to have a region as well as a sortal. And that's what I did in that account, which was, I didn't read out. But a special case, of course, is that in which the sum being considered is the sum of all of them. In that case, we can consider the set of all f's and the set of all g's and ask if they're one-to-one correspondence. If we want, therefore what we get, if we're going to have a possibly selective theory of sets, a theory of sets has to be selective realist to avoid paradox. If you don't want to avoid paradox, that's fine. You just go dialethic. But if you want to avoid paradox with your theory of sets, it'll have to be selective. And what we do in a selective theory of sets is we need some sort of axiom telling us when we have sets. So if any genuine universal, any genuine sortal universal f, and any region, and any sum of some f's, doesn't have to be a region, any sum of some f's, there will be a set of the f's which are part of that sum. Now, in many cases, this will all be fictitious. the abstract sortal, sorry, the correspondence, the one-to-one correspondence will be fictitious. For example, if we have a genuine, non-fictitious one-to-one correspondence between the F's and some of the G's, and in genuine, that's real, existing, one-to-one correspondence between the G's and some of the F's, so you go from the F's and some of the G's to the G's and some of the F's, then by the Schroeder-Bernstein theorem, there's a one-to-one correspondence between all the F's and all the G's. So even if we start off with oops, oh no, sorry, I won't move, sorry. Even if we start off with a real relations to the one-to-one correspondence between the F's and some of the G's, and all of the G's and some of the F's, the Schroeder-Bernstein theorem gives us a construction that is, it's not concrete, it just says there is such a correspondence. We won't necessarily have a real one-to-one relation between all of the F's and all of the G's. So some one-to-one correspondences are fictions. Now, when we talk about the sum of F's, or the sum of F's, sum of some F's, that's what I call a degenerate system. Javier and I discussed this, whether it counts as a system at all, but it's degenerate. But the same method of analysis, which gives us sets, can also be used to any system which instantiates a mathematical structure. We got cardinal numbers and sets. We got sets because we were looking at degenerate systems. That, in fact, is the way to characterize sets mathematically as the degenerate case of structure. But suppose now we have our sortals and we consider the sum of some F's, etc., but they're ordered. We've got an ordering on them. And then we consider something else, which is the sum of some other sortals, ordered in a different way. But suppose there's an isomorphism between the orderings, then the whole construction of cardinal numbers from the one-to-one correspondence isomorphism can be replicated for an isomorphism which is now a one-to-one correspondence that preserves order. And we go for the whole procedure, and what we get is instead of a set, we get an n-tuple. So if we were just considering the special case of pairs, if we go through the construction of sets by looking at abstract sortals, and we consider sets of twosomes, sets of pairs, unordered pairs, and we consider the isomorphism of them, they're all isomorphic, and from that we got the cardinal number 2. But if we, and the abstractly sorted sum of two things is just the set of those two things. But now if we do the whole same procedure, not with the degenerate system of just being a sum, but a system in which there is one thing prior to another with respect to some ordering, we go through the whole procedure, what we end up with is not a set, but an ordered pair. This gives us a philosophically and mathematically motivated, or so I say, way of saying what a pair is, which is an improvement on Kuratowski, which is just one instance of that sort of structure. You will notice as a corollary that once you start doing this kind of thing, you get quite high order universals. And that I think is characteristic of mathematics. And the more abstract the mathematics gets, the higher order the universals are. So if you start doing what mathematicians call category theory, which is to treat the system of all mathematical kinds as itself a kind of mathematical system, you go up even one more level of abstraction and talk about, as regards universals. In principle, there's no upper limit, though. I don't think, in fact, mathematicians deal with levels of abstraction that is more than sort of 5 or 6 orders of universals. Okay, that's the application to this of a theory of mathematics. It uses, again, abstraction, but it also uses the idea of structure. What I have also shown is how you can see that some of these structures, are going to have possible instances, some have actual instances, some have merely conceivable instances. So, if you ask what numbers there are, well, numbers are universals of a certain kind, and the ones that exist will include some very large numbers, at least the first infinite cardinal. But if you ask which have actual instances, well, maybe there's an upper limit to the number of things in the universe, however we characterize them. If the universe is finite, that might be so. If it's finite and in some sense discrete. So we might perhaps, it may be, shall we say, that there aren't any instances of the integers greater than some large number, but the ones that are greater than that are still possible. It's the same argument as we used with temperature. It's perhaps even more obvious in the case of the integers. That if we know the integers up to some point are possible because they're actual, but instances of them, I mean, but beyond a certain point, they have possible instances. But that means the numbers themselves exist as universals. But so a lot of mathematics concerns what's possible rather than what's actual at the level of the particulars. But if we're talking about the universals, these exist. But then there are other universals, or no, they're not universals, but other mathematical items are presumably, I say presumably, I mean can't prove this, fictitious. Let me tell you why I think they might be fictitious. As we examine the mathematics of infinity, we have choices. Is the axiom of choice correct or not? For example. Is the continuum hypothesis correct or not? Now, somehow, whatever's the correct answer, you have to say at some point there's a universal that does exist, and there's one that's a mere fiction. So, if the system of sets obeys the axiom of choice, then there's a universal describe the structure of that system, that type, exists. But the universal describing the type of system which is set theory without the axiom of choice, no, with set theory with something incompatible with the axiom of choice, and the incompatible axioms in its place, is a universal that doesn't exist. So some of them are going to be purely fictitious. Mathematicians can still discuss them. And that bears on the point of the question, I mean, what is the point of mathematics? Why do pure mathematics? Now, when mathematicians are trying to sell themselves, they say, oh, these things have applications. And indeed, they do have applications. Any really complicated problem in mathematics will typically have an application to cryptography. The way to provide codes typically is to find a really complicated mathematical problem that's easy to pose and difficult to solve. So yes, in principle, almost all of pure mathematics has applications to cryptography. Of course, we don't use all the applications, but there is a rather abstruse subject called the theory of elliptic curves, which was used to prove Fermat's last theorem. But it's also used in cryptography for that reason. But I don't mean that. I don't mean the applications. I mean, why study it for its own sake? And my answer is fairly brutal. It's a worthwhile thing to discover, to investigate the universals that exist, but not the universals that are mere fictions. You need to study the universals that are mere fictions merely to provide proofs, lemmas. You might be able to prove a result in mathematics that concerns genuine mathematics to do with existing universals. You might, in your proof, detour via fictional ones, and that might be a reason to study them. But the object of the exercise is to discover truths about universals that do exist. So, mathematics, I think the point of mathematics is more secure if what you are discussing is something which you think these universals do exist, they're not merely fictions. Okay, so much of the application to mathematics and the development of some of David Armstrong's ideas. Let's quickly look at a couple of problems that mathematics poses for my overall theory of things. Functions. Functions are very important in mathematics. The intuitive idea of a function is something that assigns something to something else. Instead of an operator, it does something. The intuitive idea is sort of dynamic. It's a metaphor. The dynamism is a metaphor. Okay, the idea of an operation is a metaphor. We know that. But nonetheless, we have this idea of an operator. So the square root, positive square root function operates on the number 4 to give us the number 2. Any theory, such as mine, at least at this stage, which analyzes a function as a certain kind of relation, seems to get it wrong. The positive square root function is usually analyzed as follows. You say there's a certain relation that holds, and it holds between 4 and 2, and it holds between 9 and 3. And then, of course, the same type, there's a respective resemblance here. The same type of holds, so we have this universal, the square root function. That doesn't capture the dynamism of the metaphor of a function doing something. Okay, that's a minor problem. I mean, I think if someone can turn it into a serious problem, I'd be interested. I mean, to turn it into a serious problem, you've got to do more than just talk about the metaphor of dynamism. It's the problem of unnatural entities. One good reason for, this is David Lewis's new work for universals. One good reason for realism about universals is to ground the degrees of naturalness. Okay, we know all about that. Some of the stuff mathematicians consider are too unnatural to be even fictitious instances of real universals. So we have this problem of fictitious universals. And I've already touched on this actually, but I'm now using it as an objection. So consider some idealized history of numbers. As I said, we discovered 0, or Brahmagupta discovered, someone discovered 0, and Brahmagupta discovered negative numbers. And later people discovered imaginary numbers. And then they talked about, this is where it starts getting heavy, talked about quaternions, maybe even octonions. And then we also generalized to vector quantities, and we generalize, and we generalize, and we generalize. At what point do mathematicians stop making discoveries and start telling stories? We don't know. Utility in physics is a guide, aesthetics is another guide. So I think a philosophy of mathematics shouldn't insist that everything mathematicians discuss is are genuine universals. I think some of what they do concerns mere fictions. And I think that therefore this objection can be met, but only provided we have a theory not merely of universals that exist, but of fictitious universals. That's the point. That's why it's an objection to the Aristotelian theory. That, okay, you've made a good case to say that mathematicians sometimes study universals, but a lot of what mathematicians study is not plausible universals. So what's going on? And I say you've got to have a theory of fictions to give a to account for the those parts of mathematics that are only of instrumental use. Okay, so now let me have some concluding remarks for the whole lectures. Okay. I hope I've shown, I haven't argued, but I hope I've shown it's difficult to find a satisfactory theory of possibility. I propose a version of combinatorial fictionalism, but I have to modify it in two important respects. I have to accept fictions, fictional universals, as well as fictional states of affairs. And I think that in turn requires the respects of resemblance conception of universals. And the corollary is that we need a theory of concepts, and we need a theory of things that are conceivable but impossible in terms of fictions. Another requirement, I think, of a development of combinatorial fictionalism, indeed a development of any satisfactory ontology, is that what I've called fundamental nominalism, namely that there has to be a language, Quinese, such that if we were to restrict ourselves to what we can say using a very limited range of predicates, we should go nominalist in the Quinean way. So all this stuff about mathematics being about universals and about physics requiring universals and common sense requiring universals and a proper sort of humanist theory of what a human being is requiring universals, all that stuff, which I think is important. I think universals are important if we're to understand aesthetics and so on and so forth. All that stuff, in some sense, supervenes. There's a base level at which we should be just brutally nominalist. We just say it at that base level. Now, that is as it is. I'm not saying, oh, it's really just like that. That's not what I'm saying at all. I mean, the universals are real, and the aesthetics is real, and all this superstructure is real. But nonetheless, in the sort of fairly precise technical sense, there is a sort of base ontology which I think is pretty brutal, and sort of eliminativist in character at the base. Nominalism holds. I haven't really discussed this in detail, but a redundancy theory of truth holds at that level. And I think that's a corollary of trying to investigate combinatorial fictionalism and trying to make it work. Okay, that will do.
Okay, thank you.